Okay, so I will again do it because otherwise some of students not available now. Okay, so now as I told you, we are in Fourier analysis. Okay, Fourier analysis. So Fourier analysis is actually very powerful tool to analyze signals. Okay, and so this Fourier analysis we normally used in signal analysis mainly, and system analysis also, signal and system analysis. Okay, signal and system analysis. Okay, especially as LTI system, linear time invariant system. Okay, and also we need to use Fourier analysis. We can use Fourier analysis to analyze uh, signal also. Okay, for signal processing, system designing, that kind of things. Okay, this Fourier analysis is very powerful tool. Okay, it is a mathematical tool actually. It is a mathematical tool, but it has very strong practical sense also. We will see them later. Okay, so maybe some of you have learned continuous time Fourier analysis. So you should know what is continuous time and what is discrete time. If the time is a continuous variable, it is continuous time, uncountable variable, and it is the time is a discrete time. That means if we have countable values between two time points, it is discrete time. Okay, so you should know what is continuous and discrete time basically. Okay, so in signal and system, some of you may have learned Fourier analysis for continuous time signal, but in this module we mainly focus, as I told you, for discrete time signal. Okay, we are mainly focusing on discrete time signal. As in continuous time signal, we have two techniques, Fourier series and Fourier transform. Fourier series we use for periodic, Fourier transform we use for non-periodic. Okay, so again, another signal classification, another signal type, periodic and non-periodic. Okay, so periodic means if the signal is repeating, it is period. It is a periodic signal like this. Okay, so this part is repeating, you can see. Okay, so this is one cycle. We call this repeated part is one cycle. So there is a time for one cycle. We normally refer to as fundamental period. Okay. So, so we know how to find the fundamental period. We have discussed it in sampling class. Okay. If we get two consecutive points, two consecutive repeated point, and if you measure the time between two consecutive repeating points, you can get one cycle duration. So that is how we can measure the cycle time. In other words, fundamental period. Okay. So now I take sinusoidal signal. So you can see that sinusoidal signal is also repeating, and this is one cycle. This cycle is repeating again like this. Okay. So the duration, time width of this circle is called as periodic. The fundamental period. Okay. And how to find the fundamental period? So you already know that we can select two consecutive points and measure the time value. That is how we can measure the fundamental period. Okay. So if you consider any point here, okay, any arbitrary point at t, okay. So this point will be repeating. So this is xt. Let's say that this is xt. This point is xt. Okay. This is the point, arbitrary point, common point related to t. Okay. So that value is xt because it is a function of x. Okay. Xt. Okay. Then after t time, that means after period, this point again repeating. Okay. After period, this point again repeating. So that point will be t plus, this time will be t plus t. No? So that point will be x t plus t. So these two point will be equal. Okay. So this is the condition for periodic signal. This is the condition for periodic signal. You better keep this in your mind. Okay. Okay. This is the periodic signal. This is the condition for periodic signal. Okay. And if this condition is not satisfied, it is non-periodic signal. That means signal is not repeating. If this condition is not satisfied, that means the points are not repeating. The points are not repeating. That means it is not a periodic signal. Okay? So that is the periodic signal. Okay. Now we are discussing about, we are mainly focusing about our main concern in discrete time Fourier series. Okay. So we are concerning discrete time signal. Okay. For discrete time signal, so that means sequences should be repeating. Okay. So it can be like this. Okay. So here 1, 2, 3. Maybe this one 0. Again 1, 2, 3. This one 0. Again 1, 2, 3. This one 0, like this. You can see that. This one is repeating again and again. This one is repeating again and again. Okay. So this is a discrete time signal. So I told you that discrete time signal we normally represent with respect to sample number. Okay. So it is a function of n. But don't forget, this n is related with time, NTS, that is sampling time. The corresponding time is related, corresponding sample time is related with this equation. Okay. So that is that. Okay. So, um, so in the same manner, so now this is a function of n. Continuous time signal is a function of t. So you measure the period with second time. So here, for this one, this t, fundamental period, let's say that capital T, fundamental period is measured in second. Okay, because this is a function of time, but this is function of n, sample number. So this period should be measured in n using a sample number. Okay, so how to find the period? We have already learned this. Okay, so in the same manner, you have to select two consecutive uh, point. This is one point and this is another point. Then you can count how many samples from here to here. 1, 2, 3. So here it is 3. In this signal, it is 3. Likewise, you can calculate the period. Okay, so that is very important. Okay, you should be able to calculate the period, fundamental period of the signal, discrete time signal. So very easy. You have to choose two consecutive repeated points. Then you have to count the sample number between these 2 points. That is enough. Okay. Okay. Uh, so for the Fourier series, there is identity. Okay. Fourier series, there is identity. Okay. So I will first write the Fourier series identity for uh, continuous time signal. Okay. Continuous time signal. Continuous time Fourier series. Okay. So in continuous time Fourier series, that means Fourier series, okay, any Fourier series, uh, it say that, okay, it say that any signal, any signal. So normally I use any signal, but actually it is not completely correct, okay. If I tell any signal, it is not completely correct. I will tell you why, okay. So now I will tell any signal can be represent represent as a collection of sine and cosine signal or as complex exponential sine and cosine term. You can write like this: sine and cosine term or as complex exponential term. This is the Fourier series. Any signal can be represented as a collection of sine and cosine term or as a collection of complex exponential term. Okay. So this is Fourier series representation. Actually, this any signal, it is not correct. Okay. So there is a condition. Always I can't remember that condition. Okay, I'm sorry. That is a distinct condition or something. Okay. This is distinct condition. Okay. I'm correct, I think, this time. Okay. So actually, uh, we can represent Fourier series, okay, Fourier series, okay, if it satisfy the distinct conditions, okay. So there are some conditions. I can't remember one or maybe two or three conditions, okay. So this Dirichlet, no, Dirichlet, I think my name is not correct. It is Dirichlet, okay, Dirichlet condition, okay. So this Dirichlet condition should be satisfied if we want to represent a signal as a collection of sine terms or exponential terms. But almost all the signal we practically encountered, and so maybe some mathematical signal also satisfy that Dirichlet condition. Okay, so that is why I use this any terms. Okay, uh, so in future also I will tell like this any signal. Okay, but don't worry, there is a condition, Dirichlet condition. Okay. Okay. Now, any signal can be represented as a collection of sine and cosine term, or as a collection of complex exponential term. Okay. Okay. So we will see how we can write. Okay. So I will show. I rather than writing, I will show the equation. Okay. So those equations are in many books. Okay. Mm, so I will use your reference book. So that reference book is used by Dr. Udesh also. Okay. So I think you can download that reference book from the LMS, okay? This is the reference book, okay? Hawkins book, okay? Digital signal processing, John Hawkins, okay? And so this is your reference book, okay? Now if we see the chapter, yeah, this one, frequency analysis of the signal, okay? Okay. Actually, in Fourier analysis, we are analyzing the frequency. Uh, it is some kind of frequency analysis, okay? Uh, I will tell you later, okay? So here you can read them, okay? Read them, okay? So normally, if you consider waveform, okay? So we are talking about time domain signal, okay? Time domain signal. So the signal is changing with the time. Signal is changing with the time, okay? For example, this is a sine signal. So that sine signal is changing with the time, okay? And so that maybe this can be taken from a signal generator or something. And if you feed this to oscilloscope, you can see this, okay? This is we call the waveform. This is we call the waveform, time domain signal, okay? And so for this signal, okay, this signal, so you know that this is a basic function. This is a basic function, basic signal, sorry, not basic function, basic signal, okay? One basic signal, sinusoidal signal, okay? So this is one cycle, okay? This is one cycle. So there are number of cycle per second, that is we call frequency, okay? So if this is a periodic signal, there is a frequency, definitely, okay? So I told you, maybe I have told you that if we have one sinusoidal signal, that means it has only one frequency component, we called it harmonic. We called it harmonic. Okay. One frequency component, we called it harmonic. Okay. So for a sinusoidal signal, we have only one frequency component. That is the frequency of the signal. That is the frequency of the signal. For example, if we get this kind of signal, cos 2500t, this is the frequency of the signal, and that is the harmonic, 100 hertz. That is the harmonic. We called it one tone signal also. Only one tone is there. One harmonic is there. singleton. Okay, we sometimes call this kind of signal singleton. Okay, so this is one harmonic is there. So sinusoidal signal will have only one harmonic. Okay, so I told you, and I show you, I think I show you this in MATLAB. Okay, so if I add another another signal with different amplitude and with different phase, but in same frequency, if we add many signal, is still how many frequency component in this signal has? If we get this kind of adding signal, we normally call it composite signal. Make it up again a composite signal. So if we add different signal with different amplitude and different phase, but same frequency, okay, how many frequency components are there? Here you have 100, here you have 100. That means one frequency component. If you have 100 another component, okay, uh, 1 cos 500 t, 5 cos 200 to 500 t, likewise, still it has only one frequency component. Okay, so you will get again sinusoidal signal. We see this in MATLAB. Okay, no, I think please see the lectures in sampling. Also, I explained this. If we add two more signal, we have if we have two or more signal with same frequency, sinusoidal signal with same frequency, again we get a sinusoidal signal. That means that signal has only one frequency component. But what happens if we have, this is 100t, and if it is 200t? So now you can see that there are two frequency components. So it will not be a sinusoidal signal. It will be another signal. Okay. Okay. So only sinusoidal signal will have only one frequency component. Only sinusoidal signal will have only one frequency component. Okay. Okay. So that sinusoidal signal, okay. Okay, don't get confused. Okay. I will come to the Fourier series again. Okay. Because just a reminder, if you consider one sinusoidal signal like this, 2 sine 2 500 t something. Okay. So that means this is the frequency component. This is the frequency component. Frequency component or harmony. This is the harmony or frequency component. Okay. So if you add uh, more signal, sine to 500 t, another signal, maybe 3 sine to 500 t plus 5 by 2, so on. Okay, but with same frequency. That means this signal also have only one frequency component. This also will have only one frequency component. So it will be a sine signal. It will be a sine signal. Okay. Now, if you consider another signal, let's say that this is x1t, this is x2t, x3t. Okay. So it has two components, sine 500t plus 2 sine 200t. This kind of, okay. Okay. So you can see that now it has two frequency components. This is 100, then this is 200. So there are two frequency components. Two frequency components. Okay. So this has only. So this will not be a sinusoidal signal because there are two frequency components. This is not the sinusoidal signal. Sinusoidal signal. Okay. This one sinusoidal signal, and this one also sinusoidal signal. Okay. So we have seen this in MATLAB. Okay. Okay. Now, so if you see this waveform in oscilloscope, you will see a sinusoidal signal like this. Okay. So maybe this phase shift is maybe changed. Okay. And if you see this one in oscilloscope, again you will get a sinusoidal signal like this. This amplitude and phase may be changed, but the frequency will be 100. Frequency will be 100. No any frequency change. The signal waveform will change. Okay, waveform will change because amplitude and phase will change, but frequency not change. So you have a sinusoidal shape. Here also sinusoidal shape. Now, if you watch this using oscilloscope, okay, so that will not a sinusoidal signal. Okay, so that will not a sinusoidal signal. Definitely, it will not a signal. Maybe like this or something. I don't know. Okay, so this kind of signal. Okay, this kind of signal. So if it is not a sinusoidal signal, that means there are more frequency component. More frequency component. There are more frequency component. Okay. If it is sinusoidal signal, that means there are only one frequency component. Okay. Okay. Now, what happens if you send this signal to spectrum analyzer? Anyone have that idea? If you send this signal to spectrum analyzer, what happens? Spectrum analyzer is also a oscilloscope. It is just like oscilloscope. Okay. Okay. So this is oscilloscope. Okay. This is oscilloscope. Okay. This oscilloscope. Okay. Actually, we have an input signal here. Okay. Then you can see the waveform here. Okay. And spectrum analyzer is also this kind of one. And if you input the signal here, okay, so we can see something here. Okay. So what kind of things we can see? Oscilloscope, definitely. Oscilloscope, definitely. You can see the waveform, this kind of signal, sine signal. Okay. But spectrum analyzer, what you can see? Actually, in spectrum analyzer, you will see this kind of things. Okay. So in oscilloscope, we can see the voltage changing with the time. So this is the voltage we can see. It is changing with the time. Okay. Okay. Spectrum analyzer. If spectrum analyzer, in spectrum analyzer, okay, spectrum analyzer, we can see frequency. This is time. In oscilloscope, we can see time domain signal. In spectrum analyzer, we can see frequency domain signal. Okay, this is a frequency domain signal. That means it plot frequency versus voltage. Actually, not voltage, frequency versus power. Okay, so if you see this one, okay, if you send this kind of sinusoidal signal, okay, if you send this kind of sinusoidal signal, let's say that this peak value is A, okay, this peak value is A, okay. So the power of this sinusoidal signal, okay, I will tell you how it come later, okay, A square by 2. This is the power of this sinusoidal signal. I will tell this later how this happened. Now you can remember. If the voltage is A, peak value is A, power will be A square by 2. Okay. So now it has only one frequency, 100 Hertz. And it shows the power. Okay. So the power will be A square by 2. Okay. So you will get this kind of one in spectrum analysis. Actually, it is like this. This kind of one. Okay. This kind of peak value you will see in the spectrum analyzer. Okay, in the spectrum analyzer. Okay, so this type of things you can see. So it is frequency versus power. Okay, here time versus voltage or power. Also you can plot the power also. Okay, so it is time versus power or voltage. This is frequency versus power. Power normally, not voltage. Okay, so this is called time domain signal. This is a time domain signal. We normally refer as waveform. This is frequency domain signal. This is frequency domain signal. we normally refer as spectrum. Okay, so we can see the spectrum, that means frequency domain signal spectrum, using the spectrum analyzer. That is why it named spectrum analyzer. Okay. So there are very small spectrum analyzers are also there. Okay. Also there. Okay. So we have also very small tiny spectrum analyzer also. Okay. So you can see this kind of one. Okay. So I will show if you are not still not sure, not sure, still you couldn't understand. Okay. So let's say that sine spectrum of a sine wave. So you can see that. Okay. Okay. Actually, we will get this kind of one. Okay. This kind of one. Okay. This is actually the what is we can see in a spectrum analyzer. Okay. So this is the frequency. This is the frequency. In our case, it is 100, and here it is a power. Okay. So this power may be in decibel or milliwatt. Okay. So that is the spectrum. This is spectrum. This is what we can see in spectrum analysis. Okay, this is what we can see in spectrum analysis. Okay, now tell me, okay, if you send this signal, there are two signals to a spectrum analyzer, what kind of spectrum you will get? What kind of spectrum you will get? So the amplitude. So here, by looking at this, we can't guarantee, we can't say the amplitude. Okay, we can't say that these two signal amplitudes are adding or subtracting. It is depend on the phase shift. Okay, so sometimes these two signal can be constructively added or destructively added. We don't know. Okay, so there will be any amplitude. Okay, oh, okay, there can be amplitude, and the frequency is same, 100 frequency, because here also 100, here also 100. Okay, so if you consider this signal, the same type of spectrum you will see, this kind of spectrum, but this power value will be changed sometime. Okay, this power value now the new signal amplitude is square divided by 2. This is the second signal spectrum. Okay. Okay, so this is the spectrum for plus signal, this kind of one. This kind of spectrum for second signal, this one. Okay, this is this one, this is this one. So let's say that this is a square by 2. So this will be another amplitude, a dash is square by 2. Okay, but the frequency is same, 100, here also 100. Now what kind of things we can see here? Now you can see that there are two frequency components. Okay, there are two frequency components, 100, 200, and there are two power. Okay, so here power is 4 square by 2, that is 2. Here power is, this power is 2 square by 2, that means 4 by 2, 2. Okay, so here power you will get 2. Okay, let's say that this is 3, that means 3 square, 9 divided by 2. That means you will have 4.4 milliwatt. Watt, sorry. Watt. Okay, so this is the spectrum. So this kind of spectrum you see when you see this signal. Okay, this signal, because there are several frequency components. Okay, several frequency components. Okay. Okay, now Fourier analysis said any repeating signal, okay, any repeating signal is so any repeating signal other than sinusoidal. If it is sinusoidal, only one frequency component is there. Any arbitrary signal has several harmonic, several sinusoidal signal. Okay, so it is just like our sunlight is sending through a prism. Okay, so if you are sending another type of signal, okay, another type of signal, maybe not sinusoidal signal, maybe this kind of repeated signal. So you will have several frequency components, okay. Actually here also by this prism, okay, the several the several frequency. So this color has a specific frequency. Red color has the frequency, orange color has the frequency, yellow color has the frequency. So this prism is divided the frequency component. That is we call the spectrum. Okay. And actually Fourier series also we are doing the same thing. Okay. So if we have this kind of signal and once we send it through a prism or in Fourier analysis, we can get the different frequency harmonics, frequency component. Okay, so that is Fourier analysis. Okay, so you can read this and you can get the idea. Okay, so if you have any problem, you can ask me. Okay, so actually this is the. So I told you that. Okay, I told you that in Fourier series. Okay, in Fourier series. Okay. One, any signal can be represented as a collection of sine and cosine terms. Now you can understand it because any signal has a sine and cosine terms. Okay, that means it has a several frequency component. Okay, so that frequency component can be represented using sine and cosine terms. Okay, so this is clear. Okay, and also it said that any signal also can be represented as a collection of complex exponential terms. Okay, so this is also true. Okay, why? The complex exponential terms means this one, omega naught t, this kind of one. Okay, so using Euler formula, you can write this one like this, j sine omega naught t. This is Euler formula. If this is plus or minus, this will be plus or minus. If this is plus j omega naught t, j sine omega naught t. Minus, if it is minus j omega naught t, this will be cos omega naught t minus j sine omega naught t. So this is Euler formula. This is Euler formula. Euler formula. Okay, this is Euler formula. Okay. So you can see now. Now you can see that the exponential terms has two components, cos component and sine component. Cos component has the frequency omega naught. Sine component also has the frequency omega naught. So how many frequency component here? Omega naught, only omega naught. That means 1. So e to the power j omega naught t also has only one frequency component. In other words, one harmonic. Okay. So that is why we can represent a signal as a collection of sine or cosine terms as well as a collection of complex exponential terms. Because in complex exponential term also have only one frequency component. Okay. So try to understand it. Okay. So if you have any problem, if you couldn't understand what I'm saying, okay, you can ask it anytime. Okay. So after the lecture also, you can contact me or you can send me a WhatsApp message. Oh, okay. Then I can explain. Okay. So if I don't know how to answer your question, we can contact Dr. Udesh. Okay. Okay. So don't worry. So it is very hard to directly contact Dr. Udesh. Okay. Because he's in director position, so he's very busy guy. Okay. So it is very hard to directly contact him. Okay. But you can anytime contact me. Okay. I will be available. Okay. So because I'm doing only lectures. Okay. So that is my responsibility to interact with you actually. Okay. So if you ask something, I should answer it. Okay. Okay, because if these are not understandable to you, maybe it may be my problem because maybe my pattern may be not suited for you. Okay, so it may be your problem also. Okay, so it can be we can't say who is the if you can't understand something, that may be my problem also. Okay, because maybe my teaching style is not suited for you. Okay, so you can ask it. If you couldn't understand anything, you can ask it. Okay. Uh, okay. Okay. So now maybe you can understand that we can represent this signal as a collection of complex exponential terms or as a collection of sine and cosine terms. Okay. Actually, okay. Actually, we mainly focusing on, okay, we mainly focusing on uh, to represent a signal, any signal, as a collection of complex exponential terms like this. Okay, this is we called complex exponential Fourier series representation. This is we called complex exponential Fourier series representation. And as I told you that, okay, we can use sine and cosine. Okay, so this can be uh, also represent as a collection of sine and cosine terms. Okay, collection of sine and cosine terms. Okay, collection of sine and cosine terms. Okay, we called it uh, trigonometric Fourier series representation. Okay, but mathematically this is somewhat easy. Mathematically this is somewhat easy for mathematical purposes. Okay, but this has a practical sense. Okay, because the complex signal practically not available. Practically this kind of signal not available. But this trigonometric Fourier series is practical. It has a very good practical sense. Okay, but for a mathematical purpose, this one is easy. Okay, so we are mainly focusing on this one, complex exponential Fourier series representation. That means we are going to represent a signal as a sum of complex exponential terms. Okay, so these equations are not correct. Okay, I will show them. Okay, okay. I just wrote them to give you idea only. Okay, so these are not exact equation. Okay, okay. So this is this one. Okay, this one. If you consider this one. Okay, so xt. This is any signal. Okay, so you can see that we call that linear combination of harmonic. Yeah. Okay, so if you consider this one, this xt. Okay, okay, that means any signal, continuous time signal. This is continuous time signal. Okay, so any continuous time signal, xt, we can represent as a sum of complex exponential terms. Okay, with the weightage. Okay, j omega naught kt. Okay, so this k can be from minus infinity to plus infinity. Okay, the k should be an integer. It should be a plus or minus integer, and can have minus infinity to plus infinity. Okay, so it will be minus infinity, maybe minus 3, minus 2, minus 1, then 0, 1, 2, 3, so on up to plus infinity. Okay, so it will be plus or minus integer k. Okay, so you can see that. So when you are changing this k, 1, 2, 3, so that means omega naught 1, omega naught 2, 2, 3 omega naught, 4 omega naught, likewise. Okay, so those are different frequency component. Okay, so this xt can be represented as like this, as a collection of complex exponential term. Okay, this ck we normally referred as Fourier coefficients. Fourier coefficient. Actually, this is complex exponential Fourier coefficients. Okay, but Fourier coefficients sometimes we referred as Fourier coefficients. Okay. Uh, Okay, and this omega naught is the fundamental frequency, fundamental angular frequency. It is 2.5 divided by fundamental period. This is fundamental period, fundamental period, fundamental period of the signal. Okay, this is for periodic signal. Okay, this xt is a periodic signal with fundamental period, fundamental period, fundamental period T naught. Okay. This xt is a periodic signal with fundamental period T naught, and that periodic signal can be represented as a sum of exponential terms with the Fourier coefficients. Okay. So this k can be minus infinity to plus infinity, plus or minus integer, and this omega naught, okay, omega naught, this one, we called fundamental frequency, that is equal to 2.5 divided by fundamental period. This equation is, I think you know already. You can understand this equation, okay? This is a common sense. No need to keep remember, okay? So this is T naught is uh, time for one cycle. One cycle is normally 2.5. So 2.5 divided by one cycle. So this will be angular frequency, angular velocity actually. It is measured in radian per second. This is in radian per second. Radian per second. Okay, omega naught is radian per second. Okay, and also you know that 1 over T naught is 1 over second. That is hertz. Okay, so omega naught is equal to 2.5 F naught. F naught is the frequency, normal frequency. This is angular frequency or angular velocity. This is normal frequency. Okay. So you know this equation. Okay. Okay. So this is how we can represent. Now we have a problem. We need to evaluate this CK. The CK can be evaluated using this integration. CK is equal to 1 over T naught. T naught is the fundamental period, and we need to integrate within a period. Within one period, the signal xt should be multiplied by e to the power minus j omega naught t dt. Okay, so this way you can, using this integration, you can calculate the CK value. CK value also. Okay, so these are the two equations for continuous time Fourier series representation. Okay. This is the two equation for continuous time Fourier series representation. Okay. In our module, actually here, this one we will not use, okay, but I present it, okay, to give you just a recap, okay. So this is a continuous time Fourier series, okay, and I think I have uploaded one lecture, okay, so maybe lecture 5, maybe, okay. So if you have seen it, okay, so there I try to demonstrate this relation using example, okay. Okay, I tried to demonstrate this the practical realization of this using MATLAB, okay. There I have done actually very simple things, okay. So maybe go through that lecture and try to understand it, okay. So maybe after mid-exam you can do that, okay. Now no need to, okay. And so so actually still don't worry if you didn't understand anything. I'm just explaining you the environment of it, okay. So still we didn't talk about discrete time Fourier series. Next I will come to that part, okay, very soon, okay. And I think it is better to show you that one, okay. Actually I get this one example, okay, one example from this Shom outline books, okay, Shom outline books, okay. So this book is also actually here we have only outlines, okay. That means only equations are there, outlines are there, okay. But there is no any description, okay. But this is good. This Shom outline book is good if you confuse with the subject, okay. If you have a confused with the subject, this Shom outlines may be better, okay. Because if you read this, maybe you will get more confused sometime if you couldn't understand properly, okay. But for the analysis and system analysis and system design, you need to understand these things, okay. But for the exam, I think this book is also in, okay, okay, to cover the exam things, okay. Okay, so So chapter 5 in this book, chapter 5 is the Fourier analysis. Okay. So we are talking about this one, Fourier series representation for the periodic signal. So this is I told you. Okay. So this is I told you that the condition for the periodic signal. Okay. Previously I told you. Okay. And this is the complex exponential signal, and this is a sinusoidal signal. Okay. So this can be cos or sine. Okay. That is sinusoidal signal. Okay. So this is. Okay. So any signal, any periodic signal can be represented as a collection of complex exponential terms. Okay. So that this omega naught is the fundamental frequency. It is 2 pi by t naught. Okay. Then you can also um, you can also uh, find CK Fourier coefficients, CK using this integration, but sometimes, so then if you find this CK, then you can add some value to this K. K is 0, so this K is an integer. So C naught, C1, C2, likewise, you can calculate the this weightage, then you can expand this and write this as a, you can expand this with this what is called with this coefficients. Okay. So when you are dealing with, when you try to find the zeroth component, this is C0, zeroth the Fourier coefficients. Okay. So that means at zero means K is equal to 0. So here you can see that when the K is equal to 0, e to the power 0, this will be 1. Okay. And only the coefficients is there, CK. That CK can be complex of real number. Okay. So at that time, only coefficients is there. There is no any frequency component. If there is no any frequency component, that means what? That frequency is 0. That means if the frequency is 0, that will be the DC component. Okay. So here, C naught is the Fourier coefficients for the DC component. For that one, there is no any frequency. Frequency will be 0. Okay. So 0th component you can calculate like this. What you have to do is so at the evaluation, so before the integration, you insert this K as 0, then e to the power 0 will be 1. So you have to only evaluate this integration xt within t naught. Okay. So these are the Fourier series representation for a continuous time signal. Okay. Now I have done one example. Actually, I use one example. It is in solved problem. Okay. Here solved problem Fourier series. Okay. As I can remember, I have done this example. So you can see that this we have a square waveform. This is a square waveform. So this is not sinusoidal. This is not sinusoidal. Okay. So that means there should be several number of frequency components or harmony. Okay. So using Fourier series, we are going to find it harmonics. How many harmonics? So what are the harmonics there? Okay. For that one, we are using complex exponential representation. Okay. So one complex exponent, this term will have one frequency component. Okay. So again, we can find the number of frequency component and what are the frequency component using complex exponential terms also. Okay. So, uh, so here, uh, so this is the Fourier series representation. Then you need to evaluate this CK value. Okay. To find the CK value, you need to integrate this from 0 to t naught, this xt e to the power minus jk omega naught t dt. This is the identity we have. Okay. So you should integrate within a period. Okay. So here, this one is a period, no? Because this point is repeating here. So this one is the period from here to here. That is the period. Okay. This is the period. Okay. So you need to integrate it from here to here. And also this one also period, no? Because this point is repeating here. So you can integrate from here to here because this integration you have to do within a period. Okay, this integration you have to do within a period. So any period you can choose, but it should be within a period. Okay, so it here in this example, this period is chosen because it is easy. Okay, so now you can see that 0 to t naught 2 xt is equal to a. Okay, so 0 to t naught 2 xt is equal to a, then e to the power minus jk omega naught t dt plus this integration t naught 2 to t naught, this will be 0. So xt will be 0. That means it will be 0. So this will be plus 0. Okay. So that means here no need. You have to do only this integration. Okay. So once you evaluate this integration, that is very simple integration. You know the integration of e to the power jk omega naught t. Okay. So you can get ck as this. You can get the ck as this. This is ck. Okay. But I told you that when you are measuring, when you are, so this is okay. C minus 100, C minus 200, C minus 300, any coefficients you can find, 1, 2, 3, likewise, okay, using this one. But when you are finding C naught, that is the DC component, okay, so maybe, for example, now you can see that if you apply, if you add 0 here and 0 here, what happened? E to the power 0, it will be 1. Then 1 minus 1, it will be 0. Here also 0. So 0 divided by 0, it is not defined. 0 divided by 0. So this, using this, you can't calculate C naught. Sometime it will give you undefined value. Okay. So better thing is calculate C naught separately. So you can use this one. Okay, because at that time, at the evaluation point, you make this k 0. So e to the power 0, it will be 1. So you have to integrate this one. So you have to integrate 1 over t naught from 0 to t naught only a. Okay, because you need, here we have the value 0 to t naught 2. Here we have 0. So you have this integration and value is a divided by 2. What is this value? This is the DC component. This is the DC component of the signal. This is the DC component of the signal. Okay. So that means here the frequency component is 0. No frequency component, DC component. This is DC component. Okay. Now you have a DC component. Now you have CK. Okay. So now you can expand this XT. Expand this XT. Okay. So this is a DC component. Okay. Plus these are the other components, that is minus to infinity, but this m is not, yeah, 0 also can be here, because if you add 0, that will be 1. Okay, so minus infinity plus. Okay, so you can write it as a collection of exponential terms. Okay, so if you more, it is like this. Okay, okay, I think you understand this. Okay, so it is like this, the xt. So you can see that xt is equal to sigma ck e to the power jk omega naught t. Okay, so this k can be from minus infinity to plus infinity. So now you have evaluated this ck. So it is a function of k. Okay, okay, it is a function of k. Now you can write this xt as a sum of complex exponential terms using this one. Okay, so there can be some value minus infinity. Okay, so you can write C maybe minus 2 e to the power j k is equal to minus 1 minus 2 omega naught t plus C minus 1 k is equal to minus 1 e to the power j minus 1 omega naught t plus C naught e to the power j 0 omega naught t. That means e to the power j0, e to the power 0. So this will be C naught. This is the DC component. Okay. So C naught only plus C1 e to the power j A is 1 omega naught t plus C2 e to the power J2 omega naught t, so on you can write. Okay. So C2, C1, C0 you have calculated, that is A divided by 2. Okay. So this C2, C1, C1, C2, C minus 2, C minus 1, C1, C2, C3, C4, that you can calculate using this by adding K here and here. For example, if you need to find C1, so here K is 1, that means J1, 2, 5 minus 1 minus e to the power j k is 1, 5. Likewise, you can calculate C1 value. Okay. So you can write it as a expand. You can expand. So you can see that this xt is written as a collection of complex exponential terms. Okay. So in that lecture, I do other things. What I have done is I just see that I just add these components together and check whether I can get this xt. Okay. So you can see that if we are adding more and more component, we can reach to this xt signal. Okay. So that is what I show in lecture 5. Okay. So that is also very important to understand what is the Fourier series. Okay. So that is a practical things. Okay. So you can represent, you can you can you can write any signal as a collection of complex exponential term, okay, as a collection of exponential terms like this. Then if you add those component, you will have that same signal. Okay. So that is practically verified. Okay. So that is practically verified. uh, okay. Mm. So that is it. Okay. That is it. Okay. Now we will move to discrete time Fourier series representation. Discrete time Fourier series representation. Here also we are mainly focused on discrete time complex exponential Fourier series. Okay. Now you are going to represent complex exponential, sorry, complex exponential Fourier series representation for discrete time signal. Okay. So as in continuous time signal, as in continuous time, okay, as in continuous time, this is for continuous time. In discrete time also, you can represent any discrete time signal xn as a collection of complex exponential terms like this, okay, and the coefficients is there, okay. In the same manner, you can calculate this ck. So my mistake, I have done a mistake, because this should be n. This should be n, jk omega naught n, because now we are talking about discrete time signal. So we are using n instead of t. Okay, so xn can be represented as a sum of, as a collection of complex exponential term. Okay, and here the ck you can calculate using, actually this is a discrete time value. So I told you that, maybe I have told you that, maybe you can understand that if we have a discrete value like this. Okay, so if you want to add these terms from here to here, let's say that this is 2, 3, 4. Now you need to add this term from here to here, from 1 to 3 maybe. Okay. So you can add them together, 1, 2, 3. You can just add them. You can just get the sum. Okay. But if it is a continuous signal like this, okay. So if you want to add the point from here to here, you can't simply add them because there are infinite number of points. So here you need to do the integration. Okay. So that is why actually here also we are adding those signal together. Okay. So we need to integrate it, okay, for a discrete, for a continuous time signal. But for a discrete time signal, we have separate value. So no need to integrate. We can just sum them. Instead of this omega, we can sum them. That is xn e to the power minus jk omega naught n. Okay. Okay. So now here you can see that limit is minus infinity to plus infinity, but actually no need to add in discrete time version, no need to add these terms from minus infinity to plus infinity. I will tell you why. So it will be enough to add from plus, sorry, from 0 to n naught minus 1. Here also, okay, so it should be within a period t naught. So here also same within a period that is 0 to n naught minus 1. Okay, so I will tell you why this minus 1 is came here. Okay, so this is the discrete time Fourier representation. In the same manner, k is a plus or minus integer, and this omega naught is equal to 2.5 divided by n naught. This n naught is the fundamental period. Okay. So you have to add the component from 0 to fundamental period minus 1. Okay. So that is enough. Okay. Okay. So that is discrete time Fourier series. Discrete time Fourier series. Okay. That is discrete time Fourier series. Okay. Now we will do one example relating this. Okay. So that part will come to your mid exam. Okay. That kind of question. So that is related with the mid exam. Okay. Uh, so there is a description actually. Okay. Okay. This is for continuous time signal. This is for continuous time signal. And this for a continuous time frequency is denoted by capital F naught. Okay. This is capital F naught. Frequency is denoted by capital F naught. So we have learned this too. Okay. For discrete time signal, you no need to use this one. Okay. Okay. Then these are actually continuous time signal. Okay. So you no need to follow this one. Okay, but to have the basic idea, okay, so this is frequency analysis of discrete time signal. Okay, so you can see that the discrete time signal can be represented as a collection of complex exponential signal with this weightage. So this is Fourier series coefficients. Okay, but here it is not from 0 to, it is not from minus infinity to plus infinity, 0 to n minus 1. N is the period. Here, n is the period. That is enough. Okay. That is enough. Okay. And this Ck, you can use to count Ck using this one, 1 over n xn e to the power jk omega naught. So it will be from 0 to n minus 1. Okay. So these are the equation. These are the identities we use to represent a discrete time signal in Fourier series. Okay, so that is called DTFS, discrete time Fourier series. Okay, okay. Now we will do one example. Okay, we will do one example. Okay, so first we will do so you can do this example. Okay, I will take one example from this one. Okay, so here you can see that chapter 6 is related with discrete time. Okay. Fourier analysis of discrete time signal. Okay. Uh, and in solve problem Fourier series. Okay. Okay. So we will do this question. Okay. So here we are given a sequence. We are given a sequence. Okay. So try to do this by yourself for a moment. You should have a general idea. Actually, if you can do, so maybe if you couldn't understand all the things we are discussing in the class, that is okay. Okay. But we are doing some questions. No, we are doing some uh, problems, okay, you need to, you should be able to um, do that problems, okay, at least we are doing in the class, okay. So that is directly related with the exam, okay. So you should be able to, you should be able to um, do the examples, at least examples uh, we are doing in the class, okay. So do this example by yourself and try to understand. If you have any problem, you can ask me, okay. So when you are go through the lecture, if so these things we are talking a lot of things now, okay. Actually, that is that knowledge. If you have that knowledge, that is okay, okay. So you can understand the stuff very well, okay. So maybe you can forget these things, okay. But basically, you should know, okay. Under DTFS, you should know these two equation, this red color equation, and how to apply them to solve the problem. Okay. So that thing you should know. Okay. Here, maybe you no need to remember this one. Okay. No need to remember this one. This will be given. Okay. But you should be able to apply and solve the problem. Okay. So we will see now. Okay. So here you are given a sequence and I ask you to find the complex exponential Fourier series representation of this signal, of this signal. Okay. So can you try to find the Fourier series representation of this signal? Okay. So you have given the identity. Okay. So this xn can be represented as a sum of complex exponential term tk omega naught, tk omega naught, tk omega naught t, omega naught t, okay, and this k from 0 to n naught minus 1, that is enough, okay. So omega naught is equal to 2 pi divided by n naught. This n naught is the period, fundamental period of the signal, okay. And you can evaluate this Ck by using this summation, okay. That is xn e to the power minus jk omega naught, so not n, okay. This is n. This one also not n. This should be n, okay. And here also it is enough to have 0 to n naught minus 1. I will tell you this why, okay, when we are doing this example, okay. So can you try to take 5 minutes and think how we can do this, okay? So first of all, what you have to do? First of all, you need to, you need to find the n naught. And what is the n naught for this signal? That is the first thing you should understand. You should find, okay? For this signal, what is n naught? What is the fundamental period? For this signal, what is the n naught? Tell me what is the n naught? Select two consecutive points, then count the number of samples. That is n naught. Select two consecutive points, then calculate the number of samples between that two consecutive repeated points. Select two consecutive repeated points. Okay. I'm recording, no? I think I'm recording, yeah. I'm recording. So can you find what is N naught? Tell me what is N naught. I told you how to find N naught. You need very easy. You need to select two consecutive point, any two consecutive point. Then you have to calculate the number of sample. Yeah, I got two answer. Okay, I got two answer. Okay. One answer is correct. Okay. So what you have to do is you have to select any two consecutive point. You can select this one, this one, this one, no, this one, this one, no, this one, this one, no, this one. Okay. So if you select this one and this one, okay, this one and this one. So these are the two consecutive repeated point. Now you have to calculate the number of sample. 1, 2, 3, 4. That is 4. And not is equal to 4. Okay, not is equal to 4. And I told you that, okay. So this signal is uh, xn is a sample signal. Okay, xn is a sample signal. So this omega naught is actually angular frequency, sorry, normalized angular frequency. This is normalized angular frequency. I told you now, angular frequency. Okay. So if you know, you need to find the frequency, that is omega naught is equal to 25f. Okay. F naught. Okay. Using this, you can find the F naught. F naught is equal to omega naught divided by 2 pi. Okay. So this F naught is normalized frequency. No? Maybe you can remember normalized frequency. Normalized frequency. F naught is actually the continuous time signal divided by the sampling signal. Okay. So it is a normalized frequency. Okay. Okay. Now you have found a node. Okay. You have found a node. Okay. You have found a node. Okay. Now you can see that this k is from 0 to n naught minus 1 only. N naught minus 1. But in continuous case, it is minus infinity to plus infinity. Okay. But discrete time, it is from 0 to n naught minus 1. You can understand it later why. Okay. So it is enough to have 0 to n naught minus 1 k. Okay. So how many coefficients are there? In our example, how many coefficients? How many coefficients? How many coefficients? How many coefficients are there? No. So k from 0 to n naught minus 1. N naught is 4, not 3. Okay, n naught is 4, not 3. Because if you consider two consecutive points, this one is repeating here again. Okay, this one is repeating here again. So you need to count the number of sample. One from here to here. So one sample, two sample, three sample, four sample. There are four samples. Between these two, there are four samples. One, two, three, four. So N naught is 4. Okay. So how many C naught are there? C value are there. Okay. So K is from 0 to N naught minus 1. N naught minus 1 means 3, 3. That means K is from 0, 1, 2, 3. So there are 1, 2, 3, 4 coefficients. So number of coefficients are 4 here. Okay. It is easy compared with the continuous time. Okay. Because in continuous time, sometimes we have infinite number of coefficients, but here we have only 4. Okay. So what are the value? What are the coefficients you have? When k is equal to 1, you have C naught. When k is equal to, sorry, k is equal to 0, you have C naught. K is equal to 1, you will have C1. K is equal to 2, you will have C2. K is equal to 3, you will have C3. Okay. So these are the coefficients you will have. Only 4 coefficients. Okay. So can we calculate this C naught? Can you tell me what is the value for C naught? Please tell me the value. Answer. Is the value for C naught? Can anyone tell? So it is easy. Okay. So you have to use this identity. This identity. Ck from 0 to n naught minus 1, xn e to the power jk omega naught n. Here n, okay? Here n, you need to, so this is in n, no? This, can you remember? That integration is with t, time. So here, the summation should be in n domain. Okay? The time is identical to n in complex, okay? So here it is k, here it is n. Okay? So you have to use this identity. Okay? So C naught you can easily calculate. Okay. So what is that? Okay. So C naught is when the k is equal to 0. Okay. So n is from 0 to n naught minus 1. That means 0 to 3. Okay. 0 to 3 xn e to the power j, k is 0. Omega naught n. So it is e to the power 0. So you will have e0 quantity. Okay. So what is C naught? C naught you have to add this from 0 to 3. That means x3, x0 plus x1 plus x2 plus x3 up to x3. So what are the x0, x1, x2 value? This is x0. This is 0. This is x1. That is 1. This is x2. That is 2. This is x3. That is 3. Okay. So you have to add up to here. From here to here, these samples. If you add this sample, what is happen? So that is this sample. No? This is repeated sample. So you have to only add only this sequence from 0 to 0, from 0 to 3, this value. That is why it is up to 0 to n naught minus 1, not up to n naught. If you get it up to n naught, you have to add this one also. So this is not necessary because this one is already added. This is two repeating. Okay. So this is one cycle actually. From 0 to n naught minus 1, 0 to 3, 0, 1, 2, 3. So you can easily calculate it. C0, C1, C2, C3. C0 is C1, 2, 3, 6. So how to calculate C1? Can someone calculate C1? So how to calculate? The same thing you have to use. Okay, this one. This one you have to solve. K is equal to 1. K is equal to 1 now. C is 1. Okay. So you can calculate n from 0 to 3. It's n. This time this part will not be 0. E to the power minus j. K is 1. K is 1 omega naught n. Okay. So now n from 0, that means x0, e to the power, n is 0, that means e to the power 0, plus x1, e to the power minus j omega naught, n is 1, that means minus j omega naught, plus x3, e to the power minus j omega naught, n is 2. Here n is 2, okay? So it will be minus j, n naught is 2, no? 2 omega naught, plus n is 3, that means x3, e to the power minus j 3 omega naught. So this is okay. So this omega naught you know. Omega naught is equal to 2.5 divided by n naught. Okay. Omega naught is equal to 2.5 divided by n naught. This one. Omega naught is equal to 2.5 divided by n naught. Okay. So n naught is 4. No? N naught is 4. That means this omega naught is equal to 2.5 divided by 4. That means 5 by 2. Okay. So you can add that 5 by 2 here. Okay. So you will have x0 is 0, e to the power 0, that is 0. So 0 plus x1 is 1, e to the power minus j, omega naught is 5 by 2, 5 by 2, plus x2, that is 2, e to the power minus j, 2 omega, 2 omega. 2 omega means 2, 5 by 2, 2 pi by 2 plus x3, that is 3, e to the power minus j3 omega naught is 5 by 2. Okay. So you can calculate this one. You can use zero formula. So it will be cos 5 by 2 minus j sine 5 by 2. Cos 5 by 2 is 0. This is 0 and minus j sine by 5 by 2 is 1. So this will be minus 2. This will be minus 2. So here also you can use Euler formula and you can calculate, or you can use the MATLAB, or you can use a calculator to calculate them, and this one also you can calculate. Okay. So C1 you can calculate. Okay. C2, how to calculate C2? In the same manner. Now K is 2. So C2. So you need to evaluate that summation from 0 to 3, 0 to n naught, xn e to the power minus j. Now K is 2. 2 omega naught n. Okay, e to the power 2 minus omega naught 10 minus j 2 omega naught 10. Okay. Then, okay, then you can expand this in the same manner. X0 e to the power j 2 omega naught n is 0 plus x1 e to the power j minus j 2 omega naught is 5 by 2 n is 1. Okay, plus x2 e to the power minus j 2 5 2 5 by 2 n is equal to 2 plus x3 e to the power minus j 2 5 by 2 k is 2 5 by 2 n is 3. Okay. So x1 you know it is 1, x2 you know 2, x3 you know 3. Okay. Then e to the power minus j 2 5 by 2 you can calculate using Euler formula in the same manner. So what you need to know is you need to know the sine and cosine wave. Then you can calculate. Okay. So directly you can use MATLAB and you can use uh, calculator to calculate this one. Okay. So in the same manner, try to calculate this C3 also and get the value. Okay. So answer is there. Okay. Answer is there. Okay. Mhm. Okay. Okay. This is the answer actually. This is C0, C1, C2, C3. Okay. So I have done mistake. Okay. So here this should be 1 by n naught. Okay. This should be 1 by n naught. Okay. So this whole term should be divided by 1 by n naught. That means 1 by 4. This one also 1 by n naught, 1 by 4. This one also 1 by n naught, 1 by 4. Okay. So this whole terms should be divided by 1 by 4. That means this one 1 by 4, 6 by 4. Okay. So this term also should be divided by 4. Should be multiplied by 4. This one also 4. Okay. So don't get confused. Okay. So here it should be 1 not 1 by n naught. I forget that term. Okay. No one remind me. Okay. So here 1 by 4 is there. Okay. So you can calculate this value. Okay. So just try to evaluate this. Okay. So it is very simple. Okay. And also try to evaluate this one also. Okay. Try to evaluate this one. And the answer will be there. Okay. The answer will be there. Okay. Now, uh, also try to evaluate this one and this one also. Okay. This one and this one also. Maybe this one you have to use the Euler formula. You can directly use the Euler formula. Okay. So the maybe answer is there. So try to understand this by answer. I will do it later. Okay. I will do this. Okay. In next, so we will have the session in this Sunday also. Okay. So in Sunday class, I will do this 2 question. Okay. Then I think now this one you can do by yourself. Okay. This one you can do by yourself. Okay. So what you need to know, you need to understand what is a node. Then you can add, you can do this one. So try to do this one. Okay. Try to do this one. Okay. And you can see that compact form is derived here. Okay. So maybe it is hard to get this compact form. Okay. To get this compact form, you can use, actually I am using Taylor series. Okay. Using Taylor series, you can get this. Okay. Taylor series. Or you can use what is called ගුණෝත්තර ශ්‍රේණි කියලා දෙයක්. Okay. ගුණෝත්තර ශ්‍රේණියක්. හරි. So when you get this, you will get multiple series. I don't know. Okay. ගුණෝත්තර ශ්‍රේණි. ගුණෝත්තර ශ්‍රේණි වලට මොකක්ද කියන්නේ? සිංහලෙන්, ඉංග්‍රීසියෙන්. Anyone know? What is the English words for ගුණෝත්තර ශ්‍රේණි? Multiple series or something? I don't know. Okay. So actually when you write this CK, it will kind of Gunottama Shreni, multiple series. Okay. So you can use that. So it is adding number of n terms. Okay. So you can get this kind of compact one very easily. Or you can use Taylor series expansion. Okay. So try to get this one. If you couldn't get this, that is okay. But you should be able to evaluate this C0 term. Okay. C0 term. So try to do it. Okay. So try to do it. Okay, so we will see it next week if you couldn't do it. Okay, and also try to do this one also. Okay, so that is for Fourier series actually. Okay, that is for Fourier series. Okay, I told you that we have two one. Okay, we have two things. Okay, that is Fourier series, and Fourier transform. Fourier transform is for non-periodic signal, Actually, here also the same thing is there. Okay, so here periodic signal can be represented like this. Periodic signal can be represented like this. Okay, so you can see that this k omega naught is the frequency component. Okay, so this is a summation. So this k omega naught is the frequency component or harmonic of each. Frequency component is of each. Okay, for periodic signal, for non-periodic signal, we consider this k omega naught, that is the period, the frequency, are very long, very near. Okay, very near. So this is an integer of this k is an integer 1, 2 like this. Okay, so omega naught is, let's say that 100. So you will have 100, 200, 300, 400, 500, that kind of frequency component. So these are discrete frequency component. Okay, so for the periodic signal, this k omega naught, this k will be not a discrete value. Okay, so it is just like a continuous value. That means this has very small value, 0.0001 likewise. Okay, so this k omega naught, if you multiply it by k omega naught, okay, actually this omega naught is very small. We can consider for a periodic signal, non-periodic signal, this omega naught is very small. Okay, so k omega naught, 1 omega naught, 2 omega naught, these are very small value and these are very near value. Okay, for in that case, 100, 200, so there are 100 difference, very big difference. But here the difference will be some decimal point, some decimal value. So for a periodic signal, this will look as a, what is called continuous value. This will look as a continuous value. This number of harmonics. Of harmonics will be a continuous value. So it is normally representing omega, not k omega naught. So these are discrete value. So that is omega, continuous value. Okay. So Fourier series, you know what is the, so we have two points, two things. Okay. You have two things. One is Fourier series, okay, another one is Fourier transform. This is for periodic signal. This is for non-periodic signal. Okay, and this is Fourier analysis. Okay, and now you know the Fourier series representation, complex exponential Fourier representation. That is Ck e to the power jk omega naught n, and this Ck you can calculate using 1 over n naught sigma 0 to n naught minus 1. Here also 0 to n naught minus 1. Here k is equal to 0 n naught minus 1. Here n. Okay, xn e to the power here minus jk omega naught n. This is the identities. Okay, so for a continuous, for non-periodic, this k omega naught will be it is just like a continuous term. Okay, continuous term. Okay, so it will be xn will be, sorry, so it is just it is actually just directly, it is just like directly we can convert. Here we have n, the n value, no? Okay, so ck we are finding the coefficients with respect to exponential term. Okay, coefficients is multiplied by the term, then we can write the harmony. Okay, so here also we have xn signal, and we have divided it to the frequency component like this. Okay, frequency component like this. Okay, so one frequency component is there, another frequency component like this. We have divided into frequency component. Here also we are doing the same thing. This xn we divided into frequency component, okay? But these frequency components are very near to each other. These are very small values. So these are very near to each other, okay? So this will be, these components are just kind of not separate value. We will see them as a continuous value, omega, okay? So here you have separate value, but here you have some kind of continuous value. So once you get the Fourier transform for the non-periodic signal, so you will get a function with omega, not n. N is a time function, but omega is a frequency function. Okay. So that is the idea. Okay. That is the idea. So if you have any discrete time signal and if you get the Fourier transform, this will become omega function of omega. Okay. Okay. It is represented as Fourier transform of xn. So once you get the Fourier transform, this n will be omega. This n will be a frequency. Okay. So this time domain, this is a time domain. Then you convert it to frequency domain. And if you get the inverse Fourier transform, this frequency domain, you can uh, uh, convert to time domain. Okay. So if we get the Fourier transform, that will be a frequency domain signal, omega. Okay. So it is given as, I can remember, it is from minus infinity to plus infinity. It is minus infinity to plus infinity because they are n. Okay. So then n can be anything. Okay. So it will be xn e to the power minus jk omega naught n. So minus j, this k omega naught will be omega because it is a continuous. It is look like a continuous minus j omega n. Okay. So this is the identity for Fourier transform. Okay. So this is for non-periodic signal. So if you are given an non-periodic sequence and you have to ask to find the Fourier transform, it is very easy. You have to use just this identity and you need to get the summation. That is enough. Okay. But for that function, you have the omega value. Okay. You have the omega value. Okay. We will see this equation is correct or not. Okay. So this is for non-periodic signal. Okay, you see this equation will be there, this one. Now we are in a periodic signal. Yeah, this one. This is Fourier analysis for discrete time aperiodic signal. That means non-periodic signal. Okay. So this is xn. Okay. Actually, this is for this is the inverse Fourier transform. Okay. This is the inverse Fourier transform. This is what we learn now. So if we get the Fourier transform of xn, okay, if we get the Fourier transform of xn, if we get the Fourier transform of xn, if we get the Fourier transform of xn, Fourier transform of xn, so it will be x omega and it is equal to this one, xn e to the power minus j omega n minus infinity plus infinity. Okay, so xn, if you get the Fourier transform, it is x omega. Okay, this is Fourier transform. And if you get the inverse Fourier transform, Okay, this is omega will be xn. Okay, so if you get the x inverse for it, f minus 1 of x omega, then you will have xn. So that is this one. Okay, actually this omega is not discrete value. This omega is not discrete value. This n is discrete, that is okay, but this omega is not discrete value. So okay, at the definition we see, we called it, it is a continuous value. It is a continuous value. Okay, so it is not what is called, it is not a discrete value, it will be a continuous value. Okay, so uh, once you get the Fourier transform of a signal, you will get omega. Okay, so I will do one example and I will stop. Okay, very quickly I will do. Okay, let's say that you are given non-repeated sequence xn. Let's say that you are given 1 2 0 1 2 like this. Okay? So this is the zeroth sample. This is the zeroth sample. Okay, so if I go the graph, it will be like this. 0 will be 0, and this will be then -1 -2. So -1 sample will be 1, -2 sample will be 1. Okay, so this dimension is also maybe there. Okay, so normally for a zeroth value we put a mark, arrow mark. Okay, so -1 -2. So this will be then 1 2. So it will be 1 2. So it is 1. The value will be 1 2. So I will put another value maybe. Okay, so let's say that this is 4 2 and this is 2 4. 4 2 2 4. Here this will be 4, -2 will be 4, -1 will be 2. The 0 will be 0. So plus will be 2, minus plus 2 will be 4. Okay, so this is the sequence. Okay, this is not repeating. Only this one. We have only this one. Okay, this is not repeating. It is from minus infinity to plus 2. Okay, now you are asked to find, the discrete time Fourier transform. We normally call it DTFT, discrete time Fourier transform of xn. That means you need to find the Fourier transform of xn. You need to get the Fourier transform. So it will be a function of omega, x omega. This is an non-periodic signal, x omega. Okay. So that means if you get the Fourier transform of xn, that will be x omega, and it is given sigma from infinity to minus infinity to plus infinity xn e to the power minus j omega n. Okay, so this is so very easy. Now you have only sequence from -2 to 2. Okay, so you have -2 to +2 xn e to the power minus j omega n. Okay, so what is the Fourier transform? Very easy. Okay, so it will be x omega, function of omega. Normally, this Fourier transform we denote in capital X. Okay, frequency domain signal, capital X. X omega is equal to, you have to expand this, x minus 2 e to the power minus j omega, n is -2, plus x minus 1 e to the power minus j omega minus 1, plus x0 e to the power minus j omega, it means 0, plus x1 e to the power minus j omega, n is 1, plus x2 e to the power minus j omega, n is 2. Okay, so this is x omega, Fourier transform. So now you can find x omega. X omega is equal to x minus 2. X minus 2 is 4. X minus 1. X minus 1 is 2. X0, that is 0. X1, 2, X4, 4. Okay. So x minus 2, that is 4. E to the power minus minus, it will be plus. E to the power j 2 omega plus x minus 1, that is 2, no? X minus 1, 2. That is 2 e to the power minus minus again plus, so plus j omega plus x0, that is 0, so that part will cancel. X1, it is 2 e to the power n is 1 minus j omega plus x2, that is 4 e to the power minus j omega. Okay, so now you can see that this omega is a function, this omega is the variable here. This omega is the variable. Omega is the angular frequency. So this capital X is a function of omega. So we convert that xn time domain signal into x omega frequency domain. Okay, using Fourier transform. So if you get the inverse Fourier transform of x omega, again you can convert it to xn. Okay, so this is the Fourier transform. Okay, so now basically you know how to evaluate. If I give you a sequence, how to evaluate Fourier series and Fourier transform. Okay, please go through this lecture. I will upload this today. Okay, today or tomorrow. Okay, please go through this lecture before uh, Friday, before uh, Sunday. Okay, before Sunday. And if you have any problem, actually, I have sent it. I have sent it through uh, email. Didn't you get it? Didn't you get it? Okay, I have sent it through. So maybe I have some limited number of emails. Okay, so I have sent that, and I hope those will share with you, all of you. Okay, please share it. Okay, all of you one. Okay, so anyway, if you didn't get if anyone didn't get the recordings, please send me your email. Okay, you have my number now. That is my WhatsApp number is, you can call this, no problem. 8644 612. This is my WhatsApp number. Please send me a message. Okay, your registration number will be enough. Okay, then I can get the email address. Okay, send your registration number. If you didn't get the recordings, then I will send it to you. Okay, okay. So please go through this lecture. Okay, at least this lecture. Okay, before uh, before next Sunday. Okay, before next Sunday, go through this lecture. Then try to do the example homework I told you. Okay, so try to do it. Okay, so we will discuss them in this Sunday if you couldn't do them. Okay, and also and the Fourier transform also I will use this one. Okay, so I will ask you to do this too. Okay, and the Fourier transform also to practice. Okay, to practice maybe this is some hard. Okay. Okay, so try to evaluate the Fourier transform of this one. Okay, so there are 1, 2, 3, 4, 5 sequence. Okay, so try to evaluate the Fourier transform of this xn. Okay, and try to get the answer. Okay, so answer will be there. Okay, okay. So try to get it, and we will do it in next class. Okay, okay. So we will stop, uh, and I think it is better if you can mark the attendance also before leaving. Okay. So actually two students already left now. Okay. So if you have, if you please put to the group, so sometime attendance will be checked. Okay. Actually, I don't care about the attendance. Okay. But I don't know the management things now. Okay.